Hi, my name is Philip, and I'll be presenting our work on the automated assessment of vulnerability exposures. This work targets the vulnerability analysis problem faced by entities in their vulnerability and patch management programs. Entities are overwhelmed with thousands of vulnerabilities a year applying to hundreds of different assets. Then they will use some risk scoring to prioritize the work of mitigating the vulnerabilities. This may be the Common Vulnerability Scoring System, or CVSS score, or some other prioritization score. However, the goal of vulnerability and patch management is to prevent an adversary from exploiting a vulnerability and causing some damage to the system. Likewise, we model the problem as a network attack by a given set of adversaries. The automation consists of both determining whether each vulnerability is reachable and secondly, exploitable. This work has its origins in attack defense trees and network attack graphs. However, much of the work in attack trees applies more generally to adversaries and defenses and produces many outputs. There have also been a lot of work in automating vulnerability analysis, but the output is often a risk score and requires further analysis to act. So our work uses network attack graphs to target the specific problem of vulnerability analysis and produces a binary safe state analysis, which means operators can act to mitigate the vulnerability without further analysis. We start by first determining whether each vulnerability is even accessible to the adversary over a network. In many cases, firewalls prevent vulnerability exposure, but an entity may have dozens of firewalls deployed with each with many hundreds to thousands of rules. And this makes it difficult to prove a vulnerability is unreachable by a set of adversaries. We model this problem using the firewall rule sets and the zonal representation of the network. Adversaries have access to external network zones, such as the internet and enterprise networks, and then they may extend their access based on the firewall policies. An adversary may have direct access to a vulnerability within their network zone, or they may have the ability to extend access using interactive network services such as SSH and remote desktop protocol, and thereby extend their reach into other network zones. The output of our reachability analysis includes first a set of adversary and network zone tuples. An adversary mapped to a network zone means they have reachability to all vulnerabilities in the network zone. Additionally, the output includes a set of tuples for an adversary, a destination host, and the network service. This indicates which network services are reachable by a given adversary. And in this latter case, the adversary being outside of the network zone of the target asset. And I should mention here that an unreachable vulnerability is considered safe in our model. Now, for reachable vulnerabilities, we further perform an exploitability analysis. The exploitability analysis determines whether the adversary has ability to exploit a given vulnerability on a given target asset. Here we use the CVSS features, but instead of a risk score, we produce a deterministic state safety analysis. The safety analysis evaluates the set dominance among the tuple of vulnerability, target asset, and adversary features. A dominating vulnerability means the adversary cannot perform the exploit, whereas when all features dominate the vulnerability, then an exploit can occur, and the vulnerability state is considered unsafe. Then for additional granularity in unsafe vulnerabilities, we also evaluate the effective impact as a set relation of the tuple. The result of both reachability and exploitability analysis produces the binary safety output for a set of vulnerabilities applying to a set of computing assets. Those two steps produce the necessary result. Ultimately, if we can automate the tuple of adversary, asset, and vulnerability, then we can automate the safe state analysis. Likewise, the primary challenge in automation comes in determining reachability. First, we must model the adversary and their access in the network. And then second, the reachability analysis must determine whether the combined firewall policies limit the adversary's access to the vulnerability. And then finally, the relation between vulnerabilities, target assets, and adversaries exist in the network services. For example, if you consider a vulnerability in a database server, an adversary reaching the vulnerable network service depends on whether the firewalls permit such access. However, public vulnerability repositories do not provide network service data, and this is the fundamental barrier in automating the reachability problem. So to overcome this last challenge, we automate the extraction of network services through a pipeline of machine learning and natural language processing. The machine learning uses the CVSS data, the software vendor and product names from the vulnerability, and the common weakness enumerator associated with the vulnerability. Those are the input features. These features are useful for determining both web and a type of vulnerability we refer to as client network services, so both web and client output categories. Which means the client service means a user needs to interact locally with the vulnerability. A large portion of publicly reported vulnerabilities fall under these two categories. The reason machine learning works so well is because several of the features, the input features, have a strong correlation to either a web or client network service. As an example, cross-site scripting and SQL injection, common weakness enumerators strongly determine that a vulnerability is associated with a web network service. Similarly, vulnerabilities requiring local access or having product names such as Google Chrome or Adobe Acrobat strongly indicate a client must interact with the computer to exploit the vulnerability. Other network services are harder to determine, and for this, we use a feature of natural language processing known as named entity recognition, and we use that over the vulnerability descriptions. Vulnerability descriptions have proven very consistent in their language structures, which makes it easier to identify these named entities, such as network services, weaknesses, and software components. Now, the named entities themselves do not produce a network service that would require several thousand named entities, but instead we can develop a set of rules to associate common named entities with specific network services. In the pipeline, we have an output of inconclusive for both machine learning and NLP. The recall scores on this category must be very high through the pipeline because the model safety depends heavily on the identification of the network service. It would be better to mark a network service inconclusive and assume the worst in the network model than to falsely declare a vulnerability safe. We developed training data for 20,000 samples in the National Vulnerability Database 2017 through 2019 years. We developed that over the data set. And separately, we annotated approximately 4,000 vulnerability descriptions over that same 2017 to 2019 time period. The machine learning model is highly accurate, as we might expect, because we're not asking too much from it. Many vulnerabilities are either user interactive or associated with web services. And the named entity recognition model has room for improvement, but it gets us what we need. Using those named entities, we can derive more robust pattern matching rules to determine the network service. To test this approach, we use a more recent data set from the National Vulnerability Database. And the results from left to right on the bottom graph show improvement as more named entity recognition rules get added. With machine learning only, we can accurately identify 88% of the network services, the rest being marked as inconclusive. And this grows to 97% when we add up to 150 rules using pattern matching associated with the named entity recognition. At the same time, prediction accuracy remains mostly stable. Identifying the associated network services permits the model to assess reachability. And so we turn back to those other two challenges for automating the reachability analysis. We need to consider where adversaries might already have access in the network. In our sample network problem set, we make some realistic assumptions that adversaries have partially penetrated, and in our example is the control system network in the power sector. So there are clearly highly capable adversaries on the internet. Anybody can reside on the internet, so that they're highly capable and have the ability to develop exploits that are even marked unproven. And we assume that the enterprise network has also been compromised to some extent, maybe through phishing attacks or through some other malware that commonly occurs on enterprise networks. And for this analysis, we even put a bad apple, an insider threat, deep into the network in the asset management network zone. Now, network adversary movement can be modeled using the effective firewall rule sets between the segmented network zones. And for that, we refer to the paper for that, for the analysis. Then we run both the reachability and safety analysis over the representative control system network, and we find approximately 5% of the vulnerabilities over the time span are considered unsafe. And this result remains consistent over applicable vulnerabilities in the years 2017 through 2020. And a few things to point out here. This is these are applicable vulnerabilities to the model data set. So it's not all vulnerabilities in the National Vulnerability Database, but only the ones that are installed in the sample data set size. So this is a significant improvement over the amount of work that's needed on a month-to-month basis. However, there's also an interesting phenomenon over a class of vulnerabilities that extend reachability, and we refer to these as gateway vulnerabilities. If an adversary exploits a gateway vulnerability, they may extend their reach into the network, and then we need to rerun our analysis because our assumptions have changed. So when we run the same analysis iteratively over gateway vulnerabilities in the sample data set, we see the ratio of safe to unsafe vulnerabilities almost flip. And this result demonstrates importance of quickly addressing these gateway vulnerabilities. Plus, it shows the importance that firewalls have in preventing vulnerability exploits. So in conclusion, we have developed an automated vulnerability analysis system with the potential to drastically reduce the mitigation and patching burden that entities face. The model allows entities to test vulnerabilities based on assumptions they make about the adversary. And we do acknowledge that more work is needed to further automate the analysis so that we can also make realistic assumptions about the adversary. Thank you, and I look forward to your questions.